Hello again, this is Mr. White.
And Mr. Curtis?
We're going to do the same problem we did last time, except we're going to do it with algebra. Except we're going to cut some of these pieces out, so we're not going to do the max min. This question was intended for the calculator, so we're going to do the pieces that we can do without, at least easily. Of course, you know as an SL student that if I'm going to find the max and min, algebraically, I'm actually going to take the derivative of this, set it equal to 0, and there's a lot more steps, but it was a calculator question, so we're just going to do some of these pieces without. Okay, Mr. Curtis, what do you think?
Good. So starting with the y-intercept, we know that the y-intercept has the x value of 0. So if we put 0 into the g function,
so g of 0,
and then we simply evaluate it, we will get the y-intercept.
And so we have negative 50 over negative 6, which is
25 over 3. And when we did it on the calculator, we had 8.333. It's the same thing.
So as a coordinate, so we get 0, comma, 25 over 3. And make sure that you did see it on the calculator. You saw it was positive, so make sure you keep your negatives intact and they cancel each other out. Okay.
All right. So a similar logic, the x-intercepts are when y equals to 0. So we can set the function equal to 0. And 0 equals
2x squared minus 50. Divide this other piece, x squared plus x minus 6. And this was something that I didn't learn for a long time. I wasn't very good at math. And what's the trick here, Mr. Curtis?
I would just multiply both sides by x squared plus x minus 6. And the only thing you're really interested in is the numerator, because 0 divided by anything is simply going to be 0. So we can just get rid of the denominator.
Yeah, it was quite an epiphany when I learned this back in the day. Every time you have a function, like a rational function equal to 0, you really only care about the top, because the top is when it makes it 0. So every time, just multiply by the bottom on both sides, and you're left with the top equals 0. So 0 equals 2x squared minus 50.
Okay, and from here you have two options. Either you can factor it, or you can simply bring the 50 to the other side.
I'll just do this. Okay, and then divide by 2, we get 25 equals x squared. Remember our function, we just saw it a few minutes ago. There were two x-intercepts. So some number squared, a number times itself equals 25, and so that's 5 and negative 5. Both of them together equal x. Okay?
Okay, so it asks for the x-intercept, so we should state those then as coordinates.
So we get 5, comma 0, and negative 5, comma 0. Okay?
All right. And next in the problem, it asks us for the asymptotes. So the asymptotes are either vertical or horizontal. Let's start with the vertical. I always find those a bit easier. You can't divide by 0, so there's only one thing that you have to look at, the denominator, x squared plus x minus 6.
So we have the top, and you're saying that we can never divide by 0. So what we're going to try and do is see what numbers I can put in for x so that there's a 0 on the bottom, and that's what it cannot be. So what do we get? So if I factor this bottom,
then you get x plus 3 times x minus 2.
Okay, so in essence, I cannot put in a negative 3. So if I put a negative 3, this is 0, and this is negative 5, but 0 times negative 5 is still 0. And the same thing for 2. If I put in 2, I'll get 0 times 5, which is, of course, still 0. So x cannot be negative 3 and 2. And so there's our vertical asymptotes. The function cannot be negative 3 and 2, so the vertical asymptotes are actually x equals negative 3 and 2. So this is the domain. Domain is all real numbers except for negative 3 and 2. Shouldn't write that. It looks a little like a contradiction myself.
And then x equals negative 3. You can also use your probability or your set symbol with the or. X equals negative 3, one asymptote, or x equals 2.
X equals 2.
Okay. And then next we're going to look at horizontal asymptotes. And this students always take a little while longer to learn. They're a little bit more complicated. You have three cases. One case is where the degree of your numerator is greater than your denominator. Your degree of your numerator and denominator are the same, or your degree of your numerator is less than your denominator. So in this case, they're the same, and we look at the leading coefficients.
Let me go through this real quick, Mr. Kurbis. Let's just say n is less than m always. So we have, and then the second case that you just said, we have x to the n over x to the n. And the third case is x to the m divide x to the n. This is the case we have. We're looking
Case number
at
two.
Case number 2, where they're the same. And all you do is take the coefficients of the leading term. So if this is a 3 and this is a 2, then our asymptote is 3/2. Okay.
In this case, our leading coefficients are 2 and 1. So our y asymptote, the line that it approaches, is y equals 2.
Done. And that's it.
Good.
Okay.
So looking just back there for a second, if n is less than m in case 1, what kind of an asymptote do we have there?
Okay, so the question is what's happening when numbers get really, 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 really big. So n is less than m, so this is like x cubed, and this is like x to the 5th. Well, if I put in huge numbers for x, this bottom is going to overpower the top. So this asymptote will go to 0. So this is always y equals 0. If the biggest power on the bottom is bigger than the biggest power on the top. And then we just did this one. And this one is where the biggest power on the top, like an x to the 5th divide an x cubed. This one is does not exist. There is no asymptote. It goes up and up and up, unbounded. Okay, thank you.
Excellent. So now the domain and the range.
Okay, so the domain.
So the domain, there's nothing restricted on the x according to our function. So x is all real values.
Except.
-3 and 2.
So how do I write that?
So x, or comma, x cannot equal -3, comma 2.